Okay, so welcome back. We're going to do a real quick review on cell-potential calculation. In one of the other videos, we dealt with half reactions that were transferring an equal number of electrons. In this case, I've tried to find an example of half reactions that will not transfer an equal number of electrons so we can see what's going to happen. So we've established the half reactions we should be looking for based on the electrodes that are going to be used. And so we've got cobalt and aluminum electrodes. So those are the solid forms, which means that when we go to the reduction table, we're going to be looking for cobalt solid and aluminum solid. And as we look, what we find is that the reduction half reaction for cobalt has CO2 plus 2 electrons goes to cobalt solid, and the standard cell potential on that is going to be negative 0.28 volts. The other one that we're going to be working with is aluminum, and in the case of aluminum, we have aluminum 3 plus 3 electrons goes to aluminum solid as our half reaction, and the standard cell potential for aluminum is negative 1.66 volts. So as we look at this, we need to get a positive cell potential from adding the two half reactions. Unfortunately, as we have it right now, if we were to add these two together, we're just going to have a more negative reaction. The other indicator that things are not right yet is that electrons are being taken in or absorbed in both half reactions. That's not what we want. We don't want to have ions taking on electrons in both half reactions. We need to have one half reaction taking on electrons and the other half reaction giving away electrons, which means one of these two half reactions needs to be flipped. And when we flip it, the sign for the potential is also going to be flipped. And so, as we look at this, it looks like we're going to need to flip the aluminum reaction, because in so doing, we're going to get a half reaction that is Al goes to Al3 plus 3 electrons, and now instead of that standard cell potential being negative 1.66 volts, it's going to be a positive 1.66 volts. So at this point, if all we needed to do was calculate the standard cell potential, I'd be good. I could add these numbers up. But what you may be noticing is that the electrons themselves have not yet balanced. So technically, I need to multiply this half reaction times 3, which will give me 3 cobalt-2 ions, 6 electrons, and 3 cobalt solid atoms. Down here, with 3 electrons, to get things to balance out, I need to multiply everything times 2, giving me 2 aluminum atoms, 2 aluminum ions, and again, 6 electrons. Now, if I were being asked to write the balanced equation, I would know that things are good because my electron counts are balanced. They're the same, is what I mean. So 6 electrons being taken on, 6 electrons being given off. That's good. So essentially we have reduction and oxidation. Now, despite the fact that I multiplied this equation by 3, this half reaction rather, by 3, the standard cell potential remains unaffected. And despite the fact that I multiplied this half reaction by 2, its standard cell potential also remains unaffected. So I can now go ahead and add up my values. So negative 0.28 plus 1.66 puts me at a value of positive 1.38 volts, and I have now a spontaneously discharging galvanic cell. Now, one more thing to remind you, the reduction half reaction, this one, is what's going to go into our cathode, and the oxidation half reaction, which is going to be this one, is what we're going to be writing up in our anode. So that means I would have an aluminum electrode, aluminum ions in solution. Electrons are going to flow this way over here to cobalt. Cobalt ions in solution, and then our salt bridge, and so there's our galvanic cell sketch. So I hope this helps out. Good luck putting it to use for yourselves.